series of Snap Circuits videos, we're going to look at projects 219, starting with the laser gun with limited shots, and ending with project 232, the dog whistle. So with project 219, our laser gun with limited shots, there's what it looks like in the book. And there it is on the board. And with this circuit, we've got our alarm IC with our speaker as its output, a couple resistors, our NPN transistor for control, along with our capacitor, which is working as a current delay setup, and then our press switch, which of course supplies power to the whole circuit when we press the press switch. So when we press the press switch, if we press it and hold it down, of course the alarm IC is producing the laser gun sound effect, but as it goes on, it's getting slower, and it cuts completely out. And if we immediately repress the press switch, it stops playing. Now, if we've seen from previous projects, when we use a capacitor here with a transistor, we're basically creating a current delay. So what's happening right now is when we press the press switch, our current, of course, goes through and through our resistors here into our NPN transistor, through our base or gate, and that is controlling feed for our alarm IC. But because we have this capacitor here, it's also charging up the capacitor as we're holding the press switch, and as the capacitor charges up, as I've explained in previous Snap Circuits videos with setups like this, the capacitor starts off uncharged, so it has very little resistance, and as the capacitor charges up, the resistance of it goes up. And once the capacitor is fully charged, well, then it basically goes infinite resistance and no current goes through it. And because of that, it cuts off the control flow to our alarm IC, which is why over time it gets slower and slower and then kind of cuts out. And then, of course, you can't restart it until after the capacitor has discharged some sitting here. And so because of that, that's how project number 219 works. Now we're going to move on to project 220, and that's going to be the Symphony of Sounds. So with project 220, or Symphony of Sounds, that's what it looks like in the book. And there it is on the board. And so we get our 3-volt battery pack, because we're not using 6 volts here, our speaker, 2.5 volt lamp, our photoresistor and press switch controlling the inputs on our Space War IC, but we've also got our music IC and alarm IC all interconnected here, outputting to the speaker and our lamp, so they're all getting mixed together to be outputted from our speaker, and we'll visually see at least the music IC's output on the lamp there. So we turn it on. We can hear the music IC there and playing on the light as well, and we hear the alarm IC going off and Space War IC. And again, we can change the Space War IC's output by affecting the photoresistor, pressing the press switch, as you can hear. And of course the music IC keeps repeating and stuff like that. So it symphonizes, as the project says, of all the different sounds here. So that's how project 220 is. Now project 221 simply has us changing the speaker out for the whistle chip, basically to quiet down the circuit from using the speaker. So we'll take our whistle chip, install it here, and put our 2.5 volt lamp back on. Now we turn it on, it's much quieter, but we still get our output from the music IC showing through our lamp there as it repeats. And if you can hear that, it's pretty quiet on there. But we're still changing sounds here through the photoresistor. Pressing the press switch, of course, also changes the output of the Space War IC. So that's pretty much it for Project 221. Again, all we did was change out our speaker for the whistle chip. So the next one we're going to look at, Project 222, which is our transistor amplifiers. So here we are with Project 222, the transistor amplifiers. There it is in the book, and there it is on the board. And essentially we're making use of our 1000 and 100 ohm resistors there, along with our PNP and NPN transistors, plus the red LED. And basically what we're doing here is we're showing how the amplification of transistors is used. And an interesting thing to note, although the book doesn't explicitly say this, what we've essentially created here, in a manner of speaking, is what's called a Darlington transistor, where the amplified signal of one transistor is fed into another transistor to amplify it even further, so it gets even a much higher gain. So even though, again, the book doesn't say this, we've essentially created what's called a Darlington transistor here, if you want to look up what one of those is. So what we're going to do is we're going to take our fingers and we're going to connect it between our base or gate of our PNP and across the negative terminal. And as you can see from that, we're lighting up our LED, and it's lighting up rather bright. Now, of course, we've done projects in the past where we put our fingers across the NPN here to light up the LED. But as you see, I am doing that here, and I'm just barely turning the LED on, whereas as opposed if I do it here, it turns on and turns on nice and bright. And again, that's because of my body's resistance and capacitance, your natural resistance and capacitance. So what we're doing here is I'm giving a signal to our PNP here by contacting ground and contacting the base of it here. And then that signal is going through and then being fed into our base or gate of our NPN, which is then being amplified further, because this is what we want to control as our LED. So we get a small signal here, gets that turned on, which then goes into our NPN, turns it on even more, and so we get a nice bright LED. Now, with Project 223, they call that a pressure meter. And what we're essentially going to do there is what we were doing before, but we're just ever going to so slightly be touching it. So we can start up brightly, and I'm going to start pulling my fingers away if I can get it just right here. And if you notice, the LED is flickering and kind of dim in some spots. Again, I'm not pushing on here, I'm just very, very lightly ever just touching the metal. Again, what we're basically just creating here is what's called contact resistance, as it is in the industry. This is the contact resistance you get when you turn on electrical switches and other things, and of course the contact resistance is a source of heat. That's why when you look at really big switches and stuff, they may have burn marks on the contacts because of arcing. So again, this contact resistance is a form of heat in switches and other things that open and close. So that's how Project 223 works. Now Project 224 is the resistance meter. Now this time we're not going to use the PNP, we're actually just going to focus on the NPN for this. And what we're basically going to do is just show how the input current on a transistor affects the amplification of what it's trying to operate or control, which of course in this case is the LED. So we start with our 100,000 ohm resistor. It just has us put it across our PNP here, so we're basically bypassing that. And you see our LED lights up. Now we go to our 5.1K resistor and put that across the PNP. And I don't know how well the camera is picking it up here on video, but the LED is noticeably brighter as opposed to a 100,000 ohm resistor being here. Because again, we also got the 1K resistor in series with it, so this is essentially 101,000 ohms here. And so, again, that demonstrates that the input current into our base or gate affects how much amplification of the signal of our transistor there is. So less current goes through the LED, so it's dimmer. Get more current on our base. Of course, it amplifies the signal even more, so our LED gets brighter. So that's project 224. Project 225 is our auto off night light. Here we are at project 225, the auto off night light. There it is in the book. And there it is on the board. And here we're, of course, using our NPN transistor to control our red LED, which is being mounted by a 100 ohm resistor. But then we got a press switch and our 470 microfarad capacitor connected to our 100,000 ohm resistor here. So when we turn on the circuit, our LED comes on, as we see there, and then over time the LED gets dimmer and dimmer until the LED goes completely out. And even if we leave the circuit on a long time, well, no current's going to go through the LED. It's not going to discharge the batteries. Because what has happened here, as again in previous projects, when we use a capacitor to control things, it acts as a delay because, again, current is flowing through the capacitor when it's uncharged, so it's got very little resistance, and then as it charges, that resistance goes up, less current gets through it, and because of that, less and less current goes through the base of our transistor, and thus the amplification our transistor provides to our LED gets less and less, to the point where the LED just no longer lights up anymore. And because the capacitor is now charged up, even if you were to reset the circuit here, the LED will still not come on because the capacitor is retaining its charge. Now in project 226, it's discharging caps, and basically what we do there is we take our press switch and then we press it, because what we're doing is we're dumping the energy of the capacitor through our press switch, basically shorting the capacitor out so it completely discharges. So now if we turn the circuit back on, the LED behaves normally again. And again, it will go out like before as the capacitor is charging up to the point where the capacitor again is fully charged and our LED goes out. We can just press the press switch to immediately discharge it again and repeat the cycle. So that's project 226. Discharge that. And with project 227, it's changing delay time. Now you probably have an idea what's going on there. We're going to take our 470 microfarad capacitor off the circuit, replace it with our 100 microfarad capacitor, and what do you suppose is going to happen when we power the circuit on now? Let's find out. Power on the circuit, our LED comes on, but you see it quickly goes out compared to using our 470 microfarad capacitor. Let me discharge it here. Discharge it again. And from what you can see, it's going out within seconds, while it takes a little bit longer for a 470. And again, going back to previous projects, we have a smaller capacitor here. Smaller capacitance means it needs less time to fully charge up the capacitor versus a 470 microfarad, because there's less overall charge that can be stored in this capacitor relative to the 470 microfarad here. And because of that, it charges up sooner, so the LED will end up going out sooner as well. So that is project 227. And our last project we're going to be looking at with all these variations is project 228, which is the Morse code generator. So here we are with project 228, the Morse code generator. There's what it looks like in the book, and there it is on the board. And essentially we use our two transistors, NPN and PNP, along with our variable resistor, 0.1 microfarad capacitor with a 1000 ohm resistor to have our output speaker and LED basically operate when we press the press switch, because we want to generate a tone but also have a visual indication every time we activate the press switch, because essentially we're trying to mimic Morse code here by creating a generator. So when we press this press switch down, we get a tone from our speaker, and our LED lights up there, and I can control it, of course, with our variable resistor there. And I think my press switch is on its way out, so I think I'm going to be requesting another one from ELENCO, because this one isn't quite behaving as good as I would like it to. But, you know, Morse code is a internationally recognized language. You know, you probably heard the SOS, the 3 dots, 3 dashes, 3 dots, that goes something like this. And yeah, my press switch is definitely acting funky on the current side there. Well, that's Project 228 with the Morse code generator. Now, 229 is a pretty simple thing. We're going to change our speaker out for a 100 ohm resistor, so basically going to eliminate the audio side of it. Put the resistor here, put our that back, this back. And now we get our LED there. Let me push that up. So now we just have our LED there. So we don't have the audio from the speaker anymore, but we do have our LED to give us an indication. So again, I could do the SOS like before. So SOS again, 3 dots, 3 dashes, 3 dots. So that's Project 229. Now Project 230, they call it Ghost Shriek Machine, so I need to put the speaker back on there with our LED. And I believe we also take the capacitor away. A second. Replace that with our whistle chip. Take our 1000 ohm resistor away, replace it with a 10,000 ohm resistor. Connect everything back up. Oh, it doesn't go that way. It goes this way. Or does it? Yeah, it goes that way. Connect this part here. These out already. And basically now it wants to get kind of what a ghost sound effect that will either become faint or drop out. So let's see what we've got with it at the middle. Yeah, that's pretty high frequency right there. So again, that's our whistle chip and change resistor there, affecting both the tone and even light output as well, by again also varying our variable resistor. Now the LED and speaker, I am not going to do that because that's kind of a repeat of what Project 228 itself is. Kind of basically just teaching you how to understand Morse code by having somebody else operate it and then you reading the Morse code back based on both the light and sound that you hear. So we're not going to do 231. But Project 232, they call it the dog whistle. So with that, I need to set it back up like Project 228 is. So back off with the whistle chip we go. And that, and put our capacitor back in place. To snap here. And we're going to put our 100 ohm resistor here. So instead of our 1K that we had there before, now we have only 100 ohms of resistance. So I suspect this is going to have a very high frequency output here. Let's see what happens. So start with the end there. So it's pretty low. Getting pretty high. Yeah, we've got it all the way up here. Let's see if I can. No, I can't. Because the thing about dog whistles, even though it's all the way up here, the circuit is still producing a tone, but it's at such a high frequency that our human ear cannot hear it. That's why they call it a dog whistle, because it's still producing an audio output. It's just beyond our audible range as humans to be able to hear it. But dogs and other animals have much higher ranges of hearing, and so that's why they call it dog whistle, because it's at such a high frequency that they could probably hear it while we can't. So that is Project 232, and that concludes this set of Snap Circuits videos.